Welcome back to the deep dive. Today, we are pulling back the curtain on something. Well, something kind of invisible. It's the infrastructure that makes everything you do online feel fast and seamless.
From scrolling your social media feed to your banking app.
Exactly. The topic is data structures, organizing the digital world. Now, I know that title sounds a bit like computer science homework, but stick with us.
Please do, because this isn't just theoretical. This is the actual blueprint for how modern technology works.
That speed we take for granted, finding a contact on your phone in, a split second, that isn't magic. It's just really, really good organization.
It's excellent organization.
Okay, let's unpack this. In the simplest terms, what is a data structure?
Think of it as a specialized format. It's a set of rules for organizing, processing, and storing data. It's not about what the data is.
Like a name or a number.
Right. It's about how that data is arranged inside the machine so the computer can find it and find it quickly.
And the sources give us this fantastic analogy to visualize it. The kitchen cabinet.
The kitchen cabinet, exactly. So your data is all your ingredients, the spices, the plates, the forks and knives.
And if you just throw all that into a drawer, you have the data, sure, but it's a total mess. You can't find anything.
You can't. So the data structure is the spice rack, the plate stacker, the little dividers in your cutlery drawer. It's the system that puts everything in a specific place.
So you can grab it instantly when you need it.
And that instant retrieval is everything. A well-chosen data structure is the difference between a snappy, responsive app and one that's just frustratingly slow.
What's fascinating to me here is that we're really looking at the architectural rules. It's not one size fits all.
Not at all. The blueprint has to match the mission. If you need to add and remove things constantly, you need a flexible structure. If you just need to find things at lightning speed, you need a different one entirely.
That sets us up perfectly then, because the first big decision in that blueprint is this foundational split between two major categories.
Linear and nonlinear.
Right, and these just dictate the basic arrangement. So linear it's what it sounds like, right? A straight line.
Exactly. The elements are arranged one after the other, sequentially, like people waiting in a single file line.
But then for anything more complex, like a family tree or a road map, you need nonlinear.
Because in the real world, things aren't always in a neat line. In a nonlinear structure, one element can be connected to many others.
Okay, so let's start simple. Let's start on the linear side with what is probably the foundation of almost everything, the array.
The array, it's the most basic list, but it has one really important physical property.
That all the items are stored in contiguous memory locations, which means they're literally sitting right next to each other inside the computer.
In one unbroken block. And because of that, an array's superpower is what we call direct access.
Meaning you can jump straight to any item you want.
Instantly. If the computer knows where the list starts, it can just calculate the exact address of, say, the 50th item without ever looking at the first 49.
This is the parking lot analogy in action. You don't have to drive past spots 1, 2, 3, and 4. You just go straight to spot number 5.
And that makes arrays perfect for storing things where the position is key and the size doesn't change much. The classic example is image pixels.
Because an image is just a fixed grid, you need to be able to say, give me the color of the pixel at this exact coordinate right now.
An array does that immediately. But there's a big but. What if your data is constantly changing?
Right. If I have a list of 10,000 people in an array and I need to add someone new right in the middle,
You have to physically shift 5,000 people down one spot just to make room. It's painfully slow.
so that rigidity is the problem the array creates. And that brings us to the next structure, the linked list.
The linked list basically throws out that next to each other rule. It's a sequence of elements, we call them nodes, and each node holds two things.
The data itself and
And a little piece of information called a pointer. It's just an address that tells the computer where to find the next node in the chain, wherever it might be in the memory.
so they're not physically connected, they're logically connected.
Precisely. And that's a game changer for inserting or deleting things. You don't shift thousands of items. You just change one or two of those pointers. You reroute the chain.
So this is the treasure hunt analogy. I have my data and I have a clue that points me to the next location.
Yep. It's perfect for something like a music playlist. All you need to know is what song comes next.
But there's a trade-off. There's always a trade-off.
There is. With the linked list, how do you find the 50th item in the list?
You can't just jump there. You have to start at the beginning and follow every single clue one by one until you get to number 50.
That process is called traversal. And it's so much slower than the array's direct access. So again, it all comes down to what you need to optimize for.
Speed of access, which is the array, or flexibility of modification, which is the linked list. Okay, so we've covered the basic layouts. Now let's talk about two structures that are less about where data sits and more about the strict rules for how you can use it.
The structures of controlled access, stacks and queues.
Let's start with the stack. It runs on a simple principle. IFO.
Last in, first out.
And we all get this one instinctively because of the analogy. A stack of plates.
Right, you can only add a plate to the top, and you can only take a plate from the top.
The last one you put on is the first one you have to take off. You can't just pull one out from the bottom of the pile.
You can't. And this is surprisingly important in software. That undo button you use all the time,
That's a stack.
that's a stack. Every action you take, typing a word, changing a color, gets pushed onto the top of a stack.
Mm.
When you hit undo, the program just pops the last action off the top and reverses it.
Wow. Okay, and your browser's back button too.
Same exact principle. It's a stack of the pages you visited,
So the opposite of LIFO, last in, first out, would be the queue.
which is FIFO, first in, first out. A queue is all about fairness and order,
It's the ticket counter line. You add people to the back of the line,
which is called on queue.
and you serve people from the front of the line.
DICU, first person in line, is the first one to get a ticket.
And you see this when you have like a limited resource, your printer, for example.
Perfect example. If 10 people all hit print at the same time, the printer can't handle all 10 jobs at once.
So it puts them in a queue, a print spooler.
Yep. And it processes them in the exact order they arrived, first come, first served. Stacks and queues just show that sometimes controlling the flow of data is the most important thing.
Okay, so now we move from these nice, neat lines to the more complex stuff.
Here's where it gets really interesting. We're shifting from linear sequences to nonlinear structures. This is what you need when you have to model complex relationships that just don't fit in a straight line.
We're talking about hierarchy and networks now, starting with the tree.
A tree is a hierarchical structure. You have nodes connected by branches, and it all starts from a single point at the top called the root.
And the big rule here is that every other node in the tree has to have exactly one parent.
Exactly one. And the nodes at the very bottom, the ones with no children, are called leaf nodes,
And why is this structure so powerful?
because that hierarchy makes searching incredibly efficient. When you make a decision at a parent node, you can instantly eliminate entire branches of the tree from your search.
You don't have to look at every single item.
Not even close.
The best example of this is just your computer's file system.
It's the perfect real-world example. Your hard drive is the root. Then you have folders like documents or photos. Those are parent nodes.
And inside those folders are your actual files, which are the leaf nodes. That whole structure is a tree. It's how you can logically drill down to find anything.
It's also fundamental to how a web browser understands a web page. The entire page is organized as a tree structure called the DOM, which lets it render everything logically.
But that rule, the one parent rule, is also a limitation. What if you need to model something where one thing can be connected to tons of different things with no hierarchy at all?
That's when you need the most flexible structure we have, the graph.
A graph is just a collection of nodes and the connections between them.
Right. We call the nodes vertices and the connections edges. And there are no rules, no root, no parents. Any vertex can connect to any other vertex. It's a pure network.
And that's why they're perfect for modeling real-world networks, like a social network.
Exactly. The vertices are the people, and the edges are the friendships. A graph can map the connections between any two people on the entire platform.
Or GPS maps. This is the big one.
The classic application. The cities are the vertices, and the roads are the edges. When you ask Google Maps for the fastest route, it's using a graph algorithm to find the shortest path through that massive network of roads.
So a tree is for hierarchy, how things contain other things, and a graph is for relationships.
How things connect to other things. That's
Yeah.
a great way to put it.
Okay, we've covered how we store data and model complexity. Let's finish up with the structures that are built for one thing above all else: pure speed.
The optimization boosters.
Let's start with the heap. Now, it looks like a tree, but it has one very specific rule that defines it.
It does. It's called the heap property.
Right.
In what's called a min-heap, for example, the parent node is always smaller than its children. Always.
So what's the point of that? Why force that relationship?
Because it gives you a guarantee. It guarantees that the smallest element in the entire structure is always sitting right at the top at the root node. You never have to search for it.
It's just there.
It's just there. And when you remove it, the structure automatically rearranges itself to bring the next smallest element to the top. It's self-organizing.
The analogy of the hospital emergency room really makes this click.
It's perfect. Patients arrive with different levels of urgency. The heap organizes them by priority.
So the most critical patient is always at the root of the heap, ready to be treated.
And as soon as they're taken for treatment, the next most urgent patient automatically bubbles up to that top spot. It's a dynamic priority system.
Which is why they're used as priority queues in operating systems, right? To make
Yeah.
sure important tasks get done first.
Exactly. It ensures your system stays responsive. And finally, let's talk about the ultimate tool for fast lookups, hashing.
When you hear the word instant retrieval in computer science, this is usually what they're talking about. So what's a hash function actually doing?
It's creating the ultimate shortcut. It takes your data like, say, your username, and it runs it through a mathematical function.
The hash function.
Right. And that function spits out a unique fixed size code, a hash code. And that code is used as the direct index, the direct address, for where that data is stored in what we call a hash table.
So instead of searching through a list, the computer just calculates the hash and goes directly to the location. No searching.
No searching at all. And this is why it achieves what's called O1, or constant time. In simple terms, it means the lookup time doesn't change no matter how much data you have.
So finding one item out of 10 takes the same amount of time as finding one item out of 10 million?
Roughly, yes. It's one single instant step. That's why hashing is absolutely everywhere. Database indexes, browser caches,
Password verification.
password verification, definitely. The system hashes the password you type in and compares it to a stored hash. It's an immediate lookup. It's like the perfect digital library card catalog.
So to wrap this all up, these data structures, they aren't just abstract ideas, they are the literal blueprints for how the digital world is organized.
Absolutely. They determine if an app is fast or slow, if it can handle a simple list or a complex global network.
So what does this all mean for you? Well, it means the next time you browse a web page, you're interacting with a tree structure. When your GPS finds the best route, it's a graph at work. When you hit undo, you're using a stack.
Every piece of technology we rely on is built on someone choosing the absolute best organizational structure for that specific job.
Which leaves us with a final thought for you to take away.
We saw how a heap is brilliant at managing changing priorities in real time, like in an ER. So here's the question. How might that exact same data structure be used to manage the priorities in something like large-scale AI model training?
Where new data is flooding in constantly, and you have to decide in real time which tasks are the most critical to process next.
How do you ensure the most important resource-intensive operations are always dynamically prioritized in that chaotic environment? That's a